Welcome to Renaissance Charge and Truth and Heart videos. This is Rick Friedrich, and today I want to talk to you about something that's been on my mind for over a year or two. Well, some of these things go way back. What I want to offer today is information. This is not something that I'm going to sell or could really sell. And this is for helping people in poverty, people who don't have light, and making some improvements in replacement of batteries. We're going to be using capacitors. And so what we have here is a variety of capacitors. Now, just one quick passing comment, those who like to insult me on my YouTube channel, saying that I don't get straight to the point. Well, I encourage you to actually just read the description in the title, and also in the description there you will find probably the information you were looking for, or listen to the beginning of the video and don't jump to different parts of the video without watching it straightforward. So I had to get that off my mind here. Anyway, so this idea came about from several reasons. One of the things I want to address is replacing a battery in a car with capacitor bank, which you've seen some people do, and unfortunately they're greatly mistaken, and I don't encourage that at all, and I'll get to that later on. So I want to kind of dispel some common mistakes that people are making and actually give you some numbers. I'm not going to give you all the numbers. I'm just doing a really quick video here. This time it will be quick, I hope. Anyway, so I don't have the time to calculate all the times. I will give you some calculations here for what I'm really wanting to focus on, which is a replacement of small batteries with capacitors. So I'll give you some numbers there, but regarding how much energy it takes to charge up a capacitor and so forth, there's online calculators that you can use, and they can show you what happens when you connect capacitors in series or in parallel, and what the energy you put in and what energy you put out and so forth. So that is useful information, and so forth. So we're going to get into some of that. Now, again, the main reason why I wanted to do this video for a while was because I had one business connection where a friend of mine was American Mexican who wanted to give people in Mexico the ability to read at night with light. And it may seem strange that even just right across the border there are people literally that do not have light. They do not have any technology that we have, and very, very poor people. And so instead of trying to spend money on getting them each person a free energy device or one of my motors or something, I thought, the cheapest, easiest solution, instead of giving them a flashlight with batteries that you have to constantly replace, what you could do is have in one village, one energy device, such as one of my motors or even a solar panel, doesn't matter, though that is also a free energy device, and then have one battery charging up all day, and then each family or each person in the village could have a flashlight in which, instead of having batteries like these lithium batteries that are more costly, and the problem is that I'm going to be addressing in this video is the time it takes to charge these batteries, and of course having to replace them eventually and so forth. So one easy solution is spending a little bit more money and having a lot less capacity in your flashlights and having these capacitors. And so what we're going to do is show you a little representation of the system that I want to talk about. So I thought about it, you know, I have a heart for missions. My family is involved in missions. I have several cousins that are missionaries, and my aunt and uncle were missionaries. So missions have always been of interest to me, and I would like to help people in poverty. And so one way to do, instead of giving money for clothes or food that may never get to people, give them a device like this, which is simple to make and can go a long way. It's practical. So let's go over the idea here. So typically you have a let's just look at what would be the equivalent of a flashlight. So here is a 9-volt battery and an LED that would be more suitable, well, more like 10, 12-volt LED. But so this is the typical flashlight, right? There's not much to it. You have a switch that turns it on and off. Constant current flashlight. So instead of having to bring in batteries to these people that, again, are in poverty, they don't have any money for flashlights or anything, you're wanting to help them with light. Light is a huge thing that we take for granted in the first and second world countries. And at night, you know, especially in the wintertime when there isn't as much light available, you know, it's hard to, you know, if you have to use other means of light like candles and fire and so forth, then you're very limited. So instead of providing a battery which would have to be replaced, you could provide capacitors that really, if you get these good quality, these are all Maxwell, well, most of them are Maxwell capacitors. They're super capacitors, they're ultra capacitors, and low voltage but higher capacity than your typical electrolytic capacitors and other well, this is not an electrolytic capacitor, but well, anyway, it doesn't matter what the chemistry is. These are capable of storing a lot more charge anyway. So the question is the cost. What is the cost of doing this, and really what is the benefit that you're going to get out of it in the way of how long do you have a run time? I mean, I'm running these LEDs here. These are really small LEDs, but the point is, what are we after here? Now, before we get into applying this to people not in poverty, and applying this on a higher voltage or higher power level, bigger capacitors, we'll get into that, and I'm going to say that largely this idea isn't really cost effective for bigger systems. And well, let's address that right now first. So before we get into specifically this application, let me kind of burst a couple of bubbles for a lot of people. First of all, I get calls all the time from people saying, hey, what about replacing your batteries with capacitors? So here's a 48-volt bank of these 3,000 farad capacitors. That is a lot of capacity. But is it really? I can't tell you off the top of my head exactly the amount of energy stored in this battery, or well, it is a battery of capacitors, compared to this battery of 2 volt, 1.2 volt cells, 9 volt battery, but they're very similar. There's not very much more power capability in this capacitor when you have it fully charged and then discharge it over time than what's in this battery. That may sound really surprising to people, especially these are ultra caps. This is going to run you about $1,200 for this brand new, at least. If you shop around, I got this one used for like $700 or $900, and you're thinking, well, wow, that's a huge difference. You can buy the 9 volt battery for $1 or $2 or something like that, and this, when are you going to ever recuperate the cost if you're just using it for the application? So the same thing regarding a replacement of your, like this is a 16 volt cell and you could use it for a 12 volt battery in your car. But really, would you want to do that? Now, if you're down in warm temperatures and you use your car daily, then you could, right? But if you are up here in the great, well, I'm not in the Great White North right now, but close to it. If you are up the colder areas of the country, which actually most of the U.S. becomes cold enough to make this idea not practical. And well, it's not even the cold temperatures that matters. First of all, let's look at the cost, as I was just referring to. So you have, these are about $55 a piece. And believe me, I've shopped around, looked for these, and waited for the price to come down, and they're not really budging. You know, so there's not really a solution. Do not buy the Chinese capacitors. They are absolutely junk. And believe me, I've had them blow up on me. I've had them instantly discharged. They have no real capacity. They're, you know, it's lying left, right, and center. Watch out for Chinese labels that fake the real deal. So anyway, getting that out of the way, $55 to $75 for one of these. If you're smart enough, you can spend $300 on one of these if you want to. Anyway, so if you're paying that much, you know, over $300, $350 for this set, be my guest if you want to spend that instead of a battery. Now, the second problem is that this has no real reserve capacity, because really, again, it's about the equivalent of one of these batteries right here in actual capacity. So it may give you good cranking amps for a few seconds, in which that's what ultracapacitors are great for. They can deliver high amperage very fast. They can charge very fast, and that's what the purpose of this video is, or they can discharge very fast. And for other purposes in the technology that I do, that work with, that ends up being really great. Like I mentioned in the last video, that the rate of change is one of the most important factors in my motor or any, you know, free energy device. The faster you discharge and charge an inductor and a capacitor, for example, the more of a response you're going to get that is desirable for what I'm trying to do. So that's great for ultracapacitors. That's one of the only real purposes is the fast rate of charge. They don't store the charge very long. They self-discharge. The higher quality ones less. So if you have a car, going back to the car situation, you know, if you let your car sit for a couple of days, then, and if you have any, especially any shorts in the car, terminals, then you're going to discharge your cap, and you're going to start off with a lower voltage than a car battery would normally have, and you're not going to have, you're going to have a discharged bank, right? So cost-wise, it doesn't make it worth it. And then also the actual amount of power is just a little sliver. So if you actually wanted to replace your battery, you know, which is about this size in a larger car, and believe me, I was a mechanic for many years, since I was 16 years old, and I've been thinking about car batteries all my life. So this is where it's important for me to address these things. If you wanted to get a car battery equivalent in capacitors, you'd be paying at least 10 times, probably more like 20 or 30 times the amount of money. And you would have like 10 or 20 or 30 times bigger size to actually deal with the capacity, because capacitors do not hold as much power, or they don't have as much capacity as a regular battery, lead acid battery, or otherwise. Now the lithium batteries, which we have a few here, these hold more capacity for their size, so, but they are quite a bit more expensive. So, you know, these are the kinds of things you have to decide what you want to do, how you want to spend. These do charge up pretty fast, these lithium, but there's a question about how many cycles you can really do with them, and because manufacturers change from one day to the next, you'll never know in 5 years if, you know, the quality is as good as it was when they started making them. So cost-wise, no good. Capacity, no good. So really, and this idea that we're going to do with this flashlight, really, it becomes not really that affordable to do. If you got to spend, okay, so let's go over some more points. When you have a battery, which means more than one cell, when you put two capacitors in series, you lose the voltage, or sorry, the capacity is not continued. It's not the same as it was in doing that with battery. So I could put these batteries in series, right? And a battery of actual battery cells, you know, whatever the chemistry, you have, you know, well, these are 4.2 volt cells, or whatever you want to call them. And the voltage is doubled with two in series. And the capacity stays the same. Now if you parallel them, positive to negative, positive to positive, then you double the capacity, right? And the voltage stays the same. But when you put them in series, the voltage doubles, the capacity stays the same with lithium, nickel metal hydride, nickel cadmium, alkaline, and lead acid. But not so with the capacitor. When you have, these are very dangerous, by the way, so be very careful if you ever have these. So when you put these in series with each other, as they are, your voltage will double, but unfortunately you will lose the capacity. So whereas these are 3,000 farads each, right, each cell, 6 of these, which gives me 2.7 volts each times 6, right? So I have that working voltage, but my capacity is no longer 3,000 farads. And that's a huge, simple point that you can forget. If, like, I've done that from time to time in my calculations, just completely forgot that you lose the capacity when you put the cells in series. And that is what many people who aren't really familiar with these things don't realize. So that is something, and it's, people make calculations and they go away thinking something totally different. They don't even realize that they don't have as much capacity. So in this case, we have 3,000 farad caps, right? And I can tell you exactly what that is now. And there's, like I said, online calculators. So it's right in the part number here. So 3,000 farad caps have 48 volts, or 18 of these, I guess. I think, yeah. Is 165 farads. So you went from 3,000 farad all the way down to 165. Well, that's, like, these are right here, 50 farad caps. So we're like at 3 times the size of one of these caps now. It's like, oh man, that's too bad. You know, so don't be mistaken by the math. Like, don't forget to do the right math. So that's what I want to say with the car thing, with the car battery, applying this concept on a larger scale. It's really costly. So it really doesn't pay off to do it. And now one more thing that I'm going to say before I get into this in more detail, which there isn't much to say about it, is I can't forget to mention Bonita's patents, because we're doing the historical Bonita's switches project, or whatever I called it, which I started a year or 2 ago. And in the 2 patents from 100 years ago, starting 1914 to 1918, there's a series of patents with patent applications by Benitez, Carlos F. Benitez, in which he used capacitors, and in that case they were higher voltage, and he switched them around with inductors, transformers, very rapidly, and he got a gain. He had a system that sustained itself, and that seems really hard for people to believe, because when you, for example, take a capacitor that's fully charged and one that's not, and you parallel them together, the voltage will drop in half, and the actual amount of energy stored in these now is half of what you started with. So the process of a slow, the process of paralleling 2 capacitors is a loss, a big loss. And I've shown in the past where, with my Loving Path series, the same experiment where we run a bulb between that process and the bulb lights for free, and the same amount of charge ends up in both capacitors with or without the bulb. Now that's an interesting experiment, but you still have this loss in doing that. So for Benitez to actually have a system that is constantly running just with capacitors and the load is really incredible, because he has to overcome that huge loss. And now on the other side of it, so, well, let me finish with that thought with Benitez. So he had a variety of methods where he was spinning a cylinder and rotating it quite fast, which is still relatively low frequency, but fast enough. And again, the sharpness of the discharge in the charge, the make and the break, will determine the amount of gain that you're going to get from the inductors. So it's the moment of change that gives you an output, in which he was able to power a load as well as sustain the input energy in two or three stage cycle with the cylinder. So he had a variety of different methods of doing that, and then his later patent updates and the last patent were with batteries, but they could still apply the same principles as the capacitor. Now, here's another thing that is really interesting. Tesla talked about, with his patented oil-filled capacitors, which is really interesting to read and understand what he talked about, how the influence of gas and air really was is something that he was trying to avoid completely, removing all air and gas out of a capacitor, and compressed oil. So we're talking about now Tesla's own designed capacitors that were very well made. I can't tell you whether they make the same quality capacitors that Tesla had, but he describes all the details with that. Now, my point is he was able to discharge these capacitors, which again didn't really hold a lot of energy or capacity, or however you want to define that. I mean, we're probably talking about one that was, you know, so big. Those are like 2 volts right now. He was able to discharge them so fast that he got literally hundreds of thousands of horsepower, as in his own words, out of those for a very short amount of time. So the amount of gain was like not just 1,000, but hundreds of millions of horsepower. I think even he might have said the word billions at one time. And that sounds crazy. But he said there was nothing else. I wish I had the quote in front of me, but it was just something I remembered now to say. Anyway, he said there's nothing else comparable to the discharging of a capacitor, a disruptive discharge. We're not talking about slowly trickling out the energy. We're talking about a very sharp pulse, and it's enormous amount of energy all at once. And so it is very dangerous if you do short out, a capacitor, and you can look at the spike on that and everything. But anyway, those were just a couple of miscellaneous comments about batteries and capacitors. And now let's look at this. So what I have here is our 1 microfarad or 1 farad cap here, and there's the rest of them right here, which I have them all in series. And then these ones are 5 farad, these ones are 10, and these ones are 35 farad, and then these ones are 50. And I use these for various experiments, and these, of course, as I said, were 3,000 farad, and so were these. So I have here 35 farad caps, and in series, just 2 in series to do the 5 volts approximately, or just over 5 volts. You don't want to charge these capacitors over their ratings, because they will blow up on you and they'll be damaged. And then these ones are the 5 farads. So we're going to look at some numbers here now, because I did say I was going to give you some numbers. So we have a voltmeter on here. And so the idea again is that someone has a flashlight and replaces the 3 battery cells with 3 capacitors. Now you can get these at different lengths, and you could make a bigger battery pack to last longer and give you more power. But the idea is to replace your typical 3 batteries in your flashlight with 3, or in this case, these fit, these 35 are just slightly smaller, and they would fit 2 of these 35 amp hour cells, or 35 farad cells. So you gotta be careful of. So these are actually the same size as these 50s, 50 farad, but then of course they're longer than half. So you can fit, replacement 50 farad cells. And of course, these are not your 1.2 volt batteries like you have in your typical rechargeable alkaline and nickel metal hydride and nickel cadmium batteries. So none of these voltages actually match anyway. These are about 4 volts and these are 2.7, and then of course the alkaline are 1.5 volts each cell, and the rechargeable ones are 1.2 volts. So these are kind of things that you have to consider if you're going to do this sort of thing and replace batteries with capacitors. So now what we're going to do is look at what I have here is the center terminal here, which the black wire represents the negative terminal of both of these capacitor banks. So we're going to look at each one of them separately. Right now we're looking at the bigger one, and it is actually not running off of the bigger one, it's running off of the smaller one right now. And we're going to, so we're going to run a voltage regulator here. So this is how you could prevent. So the idea is you come with a flashlight and you connect up to the battery and voltage regulator over a few seconds, and then you walk away and you've got a flashlight for hours or minutes, depending on how fast you're, like how much of a load you're going to put across it. And that way somebody like in a village, as I said, could end up not having to replace batteries, pull them out and put them on a battery charger. And if you have multiple people, they would all have to have battery chargers or replacing batteries, and it's not really practical. People wouldn't get around to doing that as much, and it would be, like I said, a lot more costly. So here somebody can come there, connect up for 10 or 20 seconds, and their flashlight's charged up, and then they could walk away, and somebody else, if you wanted to have multiple chargers, which really this is peanuts, this is like really $1 worth of parts. So you could have multiple voltage regulators. I've got a couple capacitors on here for the voltage regulator, and you could have many of these hooked up to the battery, if you had a big enough battery, um, and so multiple people could be just coming there anytime and just hooking right up there and charging up their their battery. So actually I wanted to do this for the Amish for their little headlamps, and make something for them in the same way. So there, you know, you could have this in one home, and you could use a flashlight, and even if you wanted to run it a lot more powerful, like what we're going to do here is run it so here I have a second power setting where you're running this at 2 LEDs instead of 3. And so this is going to, if we can look here, the voltage dropping a lot faster. You know, so we have quite a while till that happens. And but that's the idea. Anyway, so now let's talk about how much time it takes. We'll go over the specifics of this in a minute. First I want to cover how long it takes to charge these capacitors. So with my regulated voltage power supply, amperage power supply, whatever, it's regulated, so I can set it for 1 amp, which this is a 1 amp regulator. You can get higher amperage ones, so we'll do it faster. But it takes 10 seconds to charge these 5 farad caps, which is now no longer 5 farad because they're in series. It's about half that. So it takes, to charge this up to 5 volts, which this regulator that I use daily is a 5 volt 1 amp regulator. So it takes 10 seconds to charge these up to 5 volts when they're fully discharged. What's interesting is when you fully discharge them, they will bounce back a little bit too, so that's something that you might find interesting. And the capacitor clearly is the mystery component in a lot of ways, what it can do. Anyway, 10 seconds at a 1 amp load, 1 amp input from your battery through the regulator to charge up these capacitors, which you can then run for quite a while. So what we're going to do is just do that, since it's alright, so we're going to discharge this right now. And now you can see it's down to really low voltage, but watch when I disconnect it. It's going to start to bounce back. It's already at 0.1. It's going to be going up a little bit, so we don't really care about that. So now what we're going to do, actually that shows, oh yeah, it shows negative because I have this backwards. So now we're at 0.3. So I want to show you this. So what I've done is I've got 2 switches here that go between either one of these capacitors. So this side switch here rotates between these two capacitor banks. And then, and I'll bring this closer to the camera later on here so you can see better. But so now what I'm going to do is charge this up. You can see it's already at 0.5 volt, so we don't have that much, we don't have too much to go. And now we're going to show it go all the way up to 5 volts. How fast? So 2 volts, 3 volts, 4 volts, and 5 volts. So that voltage regulator got pretty hot because it's putting out max power, and it doesn't really need a heat sink. I use these for years. If you get a bigger one, that's like, I got 2.5 amp ones here that probably would need a heat sink if you're going to push them. Now what you can do is put a resistor between and slow it down a little bit if you want to. But you can see it took roughly 10 seconds. The last little bit takes longer, and it doesn't draw full amperage in the last little bit. So it's not really, this is not about doing this efficiently, but it is about time. It's about thinking it through, which is what I thought about. People in those places, what are they going to end up using? What would work? And this would work. So you come there, put your flashlight already has the capacitor. You just plug into these terminals, whatever. You could have banana clips or whatever. Boom, hold it there 10 seconds, walk away. You could do it faster with the bigger voltage regulator. And I mean, I only put the regulator in there so it doesn't just have a big shock and heat up your wires too much, especially when we're going up to these 35 farad capacitors. So now let's look at the system. If I run it, so I'm going to go switch over to for some reason it should have been showing me. Hold on, let's just start again. Oops. Be sure to keep your terminals in the right direction. So we're at 5 volts right now. So you can see that this will hold the 3 LEDs, which are in series with each other. It's holding it going down, you know, a 1/10 of a volt on 93, 92, 91, well, 91. So it's going to hold that voltage for quite a while. I mean, the light will go down just like a regular flashlight, and you could use the Joule thief if you wanted to do, you know, which is not actually an efficient circuit, by the way, or we could design a better circuit, better flashlight, but for now, this works. So now if I want to go, like I said, and do 2 LEDs brighter, boom, now that's more like a flashlight, and it drops quite fast with these little capacitors, right? They're just very little. But, you know, if we're just talking about doing a little reading light, you know, or just seeing, going around in the dark, you know, and a little LED can brighten your evening. Anyway, so that is the smaller bank. So so now I've dropped to a voltage that you can't, the 3 LEDs will not light up because we've dropped too low of a voltage. So now we're going to go over to the other capacitor bank, And I'm going to start off by, well, you can see that is also dropped in voltage. Let's check out the voltage of the 35, which is again not 35 anymore farad because it's in series. So we're at 432. There's just a slight bit of light on that. And if we switch over again, we're going to have these two LEDs on for quite a long time. It drops fairly slow. So it's about dropping at the same speed that this smaller cap bank was dropping with the 3 LEDs. So it's very little power with the 3 LEDs. So we're going to short this out. We're going to switch over to the other cap bank. And I'm going to just short out this wire is going to get hot. So we've already discharged these down right to 0 and so forth. We're going to see that it's going to start going back up. And now we're going to charge this up with the 1 amp. It's going to take a while. And now my voltage regulator could get nice and hot. We'll see if it blows out, if it can maintain this amount of power, constant 1 amp at 5 volts to charge this up. So now this, because it's only 1 amp, is taking longer. Now, as I said, with the regulated power supply at 5 amps, 5 volts, 5 amps, then I was able to charge these caps up from 0 to 5 volts in about 20 seconds. And I think this probably puts out a little bit more than, let's see the actual amperage here. Oops. See, now it's come down. Well, I don't know how good this ammeter is, but it's only putting out a third, 300 milliamps. So it's taking a while. Again, I could just bypass all that and go directly. Again, you don't need the regulator. It's just, do you want a big spark? And you better have thick wires. Like, these wires are not appropriate. So anyway, you can. I wanted to show at least what 300 milliamps at 5 volts, how long it takes to charge up. And you wouldn't do that. I just made this one for the smaller cap bank to show you that that's probably what you would use there. So if I go, boom, oh, wrong one. We're going to connect up. The negative is already connected directly. It's the positive that is not. So I'm going to go quickly. Now we're up to 5. Whoa, I went beyond the 5 volts because this is a 12 volt battery. So the idea of the regulator is, the other thing I forgot to mention, is it allows you to do a different voltage battery, a higher voltage battery over I should have probably, yeah, so now we're at above 5 volts and it's holding more or less, and we can disconnect it. So, you know, if you had a 2.5 amp for this size voltage regulator, 2.5 amp, then that would be fine. You know, again, if you want to do it faster, I mean, you could actually just put a resistor in series instead of the voltage regulator. But the problem is, you'd have to have a battery. You wouldn't want to have somebody overcharge the capacitor, and that's what the voltage regulator does, prevents that. So again, that would be very simple, very cheap solution. So now we'll look at running this so we have all three of these LEDs, and they're just going to hold there. They're pretty bright because I've gone over 5 volts, and they're just going to hold there pretty long. Now if I go down to the higher power, or the 2 LEDs, it's going to drop faster, and I'm pretty good with these LEDs are capable. Anyway, the idea here is not to show you how bright it is, or, I mean, I guess I could do that. So let's go back to 3. And the red LEDs are kind of deceitful because they are a lot more efficient than the other colors. So obviously you wouldn't want to use red LEDs to read. You know, again, this is not like hugely bright here, but it is something that could work. So I'm going to go now to, you know, so scary pictures. See, so that's the idea. So you can see it's going down faster. Now it's slower. So again, that's the idea. It can work. I'm talking to several people right now that are wanting to do this sort of thing with missionaries, and you know, you can do this, a really small flashlight, simple, and this would go for years. Whereas if you're trying to give people a whole bunch of batteries and have them try to manage batteries and replace them, and you're not really going to solve the problem for people who really don't understand the technology at all. But you could show them, you know, you could make a plug that only goes in one way, and you could, like I said, have a solar panel that charges the battery up all day, and that would be a real solution. So, you know, these are the kinds of things I think about, and I will try to engineer solutions, and they don't necessarily have to be the whole bit, you know, like everyone having one device. I mean, there's a lot of cost in having, you know, like any kind of free energy device is going to cost some money, but this is a solution that can give people light that we take for granted in the Western world. And hey, if, you know, some mission organizations went around giving people in poverty this solution, it would be a one-time thing. It's not like giving people food where you always have to do that, or clothing. This is something that it would be really neat to see somebody take this up as a, you know, kind of a charity drive. Hey, let's get flashlights to everybody in this country, and you know, I would like to see something like that happen. And this is just a way of doing that. You know, you think of these people you know, I know people who helped out during the hurricanes and, the hurricanes this last year, and they provided different energy sources down there because they had the connection. And, you know, in times like that, this would work too, you know, like where you could, I don't know, it's more for, like I said, people who don't have anything. And there are still a lot of people in this world that don't have any light. So think about it. So thanks for watching.